Hi everybody, welcome back. This is Soft Earth 4. The Earth is fragile. For those that are live, some time has passed. We missed last week, so we're trying to get back on track. If you're not live, you've missed no time at all. Every title is a little bit cute. This word fragile, I'm going to use intentionally, right? And we might have mentioned this in a previous lecture. But, when we say fragile in a casual or colloquial sense, we often mean something that is easily breakable, easily broken, right? And often when we think of fragility and planet Earth, oh wait, I need my green chalk for this one. We think of, you see my beautiful drawing? When we think of fragility of planet Earth, we think of that classic blue marble picture, right? The famous picture of Earth taken from outer space, where you see this vibrant planet of blue water, green continents, teeming with life, set up against the stark, black, near vacuum bleakness of space, right? And so when we think of fragility and planet Earth, what we often think of is, the idea that this is this important sealed little bubble that is very sensitive to disturbances, right? That we think of it as this very thin boundary that separates us from the oblivion. We think about within this closed system that anything that we use is resource depletion. We think about climate change. We think about ecosystems going over tipping points. Those are all things we think of when we think of a fragile Earth. When we talk about materials, fragile has a related but slightly different meaning. And I'm going to play with those meanings, right? I'm going to play with the meaning of fragile, like fragile Earth, like Earth being a planet in danger. But the material meaning of fragile is something a little bit more subtle. It basically means that materials don't stay how you put them. So, when something doesn't stay where you put it somewhere and it leaves. Fragile materials, they might stay where you put them, but they don't stay how you put them. What I mean is that you make them or place them in some configuration of molecules or particles or something, and without almost any significant energy input, those materials will reconfigure and rearrange their constituent particles, whether they're molecules or whether they're sand grains or whatever. And that happens, and when it happens, it also changes the mechanical state, the strength of those materials, right? And so when we talk about fragile materials in materials science, what we mean is materials that don't stay how you put them, that they're very susceptible to rearranging their constituent particles. And when they do that, they take on different macroscopic states of behavior. Okay? So, maybe you remember from lecture 1 all the way back, we had this kind of cartoon state space, right? The cartoon state space had the de Boer number on the x-axis, right? And so we were saying that, remember that a material, when you stress it, it has some intrinsic relaxation time where the constituents want to rearrange themselves to relieve that stress. And that's a complicated thing, but we'll just, for now, consider it some intrinsic property of the material. And we defined our de Boer number of the competition between the relaxation timescale, the intrinsic rate of rearrangement of the material under a load, and the timescale that we load it, right? And the idea here, if you remember, is that if the material relaxes very quickly compared to the speed that we load it at, then the material gets out of the way when we load it. And so to us, that looks like a dynamical definition of a fluid. And if the material takes a really long time to relax compared to the time that we take to load it, that means that we push on it and the constituent particles can't get out of the way quickly, then they break, right? And so this is a solid-like regime, right? But we also had this other situation, right? Because down here, materials that are fluid, they can either be fluid like thermodynamic fluids, which we talked a little bit about before, or they can be fluid in the sense that they appear solid to us, but they're fluid-like, like the creeping soil that we've talked about, right? So we had to acknowledge that on this axis, whether we consider it like an applied stress compared to yield stress, we also talked about this dimensionless parameter like an acceleration, like shaking a material compared to gravity, right? But whether we talk about a stress compared to yield or an acceleration compared to gravity, that we can also fluidize apparently solid materials by injecting enough energy into them, right? And so we end up in this regime where this is definitely solid. In a dynamical sense, this quadrant is fluid, but it's a weird kind of fluid because from a stress condition, this material is below its yield, below the point that it spontaneously loses rigidity and flows, right? But it's fluid because to us it does fluid-like things, and this is the regime of creep. Whereas up here, this is the fluidized regime where we shake or inject enough energy that the material loses all rigidity and it flows, right? So you are here today, all right? We today are going to live in this space. So this is not a definition that most people would give for fragile material. But what I would say is that all of the materials that I would consider fragile are apparently solid materials that nonetheless creep. So I would say creep is one of the things that fragile materials do, right? So if we talk about that, materials don't stay how you leave them. What we mean is that even without much energy input, there's going to be this reconfiguration, and that reconfiguration is creep. So just to situate ourselves in terms of the landscape, right? Because we are still trying to connect this to geophysics here. All right. Remember that we have this kind of situation. If we think about a hillside, we can have a hillside that is some depth, there's rock, and then the hillside is covered in soil, right? Gravity, of course, is acting downward, and we have the situation where this soil material can do a couple things, right? In this regime, in the creep regime, what will happen is that this soil will set up a slowly creeping velocity profile that we've talked about a little bit, okay? So gravity's pulling it downhill. It's below the critical slope or the angle of repose at which it would fluidize, so it's not in this regime, right? It's in this regime. But what we know is that under gravity, this material will still ooze downhill rates of centimeter to meters per year, right? That kind of soil is going to drag along buildings and anything else with it. And so this is a mechanically solid material that nonetheless is dynamically fluid. This is the regime of soil creep. And so soil creep itself is an important geophysical problem, right? I mean, we know that when we put houses or pipes or fence posts within the soil, that they slowly get sheared apart, right? We have to come in and realign them and replace them. And so the creep alone is important. But then, right, when we subject this creeping soil to either an earthquake or we subject this creeping soil to rain, right? So we know that we can provide some energy in terms of shaking, or we can change the stress state and drive it above yield. And at that point, it will fluidize. And when it fluidizes, right, now what happens is that we basically take a chunk of soil that detaches and flows. And when that happens, this is a landslide, all right? The reason I bring this up is that creep itself, first of all, is an important phenomenon to understand in its own right, because If the soil isn't landsliding, it's creeping. But the other thing is that creep is reconfiguring the soil particles. It's changing their configurations, sometimes into states that are stronger, that make the material stronger and more resistant to failure and flow. But sometimes the reconfigurations can make the material weaker and make it more susceptible to failure. Sometimes the same kind of motion can seemingly paradoxically do both. What I mean is that you can have soil creep that actually hardens the soil and makes it stiffer, but making that soil stiffer, remember we talked about brittle and ductile before, and we're going to talk about it again today. Making that material stiffer can mean that it takes a higher stress to make it landslide, but when you stress it high enough, it fails catastrophically instead of gradual, right? So creep is important in its own right, and creep is also conditioning the soil for landsliding, right? It's conditioning the mechanical state of the soil, changing the mechanical state of the soil so that when earthquakes or rainfall events come, the history of creep that has happened is actually going to determine whether or not those rainfall events or those earthquakes or other disturbances actually fluidize the soil and create landslides or not. So we're going to talk about a model system for the hill slope, right? And the model system is our humble sand pile, right? So we have a table. Remember the sand pile. We're dropping sand grains down on the top slowly, right? We know that the pile builds up, and then it builds up to the angle of repose. And so the sand pile is this model hill slope. So referring to this phase diagram, we know that if we tilt it above the angle of repose, that it's going to fluidize. We know that if we shake it with an acceleration that is greater than gravity, it's going to fluidize. But the question is, what does this sand pile do when we stop driving it, right? So we don't add sand grains and let them pile up an avalanche, but rather we just pour the sand pile and then stop, right? We pour the sand pile and then we just sit there and we do nothing. So if we do that, we are now in this regime. So the sand pile will behave in some way as you expect it to behave. If you pour a sand pile on the table or a pile of sugar when you're cooking and you walk away and you come back, you expect it to be right there where you left it. And you expect it to look pretty much like how you left it, right? And you're right in the sense that what you can see visually with your eye is that nothing's really changed over the timescales of a few seconds or a few minutes. But remember, lecture 1, everything flows. This apparently quiescent sand pile is not just sitting there doing nothing. It is actually creeping. It turns out to see that creep, you either have to wait a really long time, timescales of months to years, if you're paying very careful attention and tracking all the grains, or you can use some different, little more sophisticated optical interference techniques, which essentially allow you to detect displacements that are smaller than what you could see with tracking particles with a camera. And if you either wait a long time or you use these optical interference techniques, you will see that the sand pile that is apparently sitting there doing nothing is actually a writhing sea of motion. So in order to think about that, I want to think about materials first that undergo simple phase transitions, and then think about materials that undergo more complicated phase transitions. Okay, so remember that we have our classic phase diagram that we draw for water, right? And so I'll draw it here. You're probably getting tired of seeing this thing now, right? But we have temperature here, we have pressure here, and we know that here we're in the solid state. And so in the solid state, the molecules organize themselves into a nice crystalline structure. Water's got a bunch of different phases. I usually was lazy and drew this as like a cube. Usually it's some hexagonal phase, but it can be lots of other phases. I think we're up to 10 or 12 phases of ice now. I don't know. A lot of different crystals, right? And remember though, in the state that the molecules are organized in some nice orderly way and that they're jiggling a little bit, but the jiggling is not enough to break these bonds between the molecules, right? And so in this low energy state, the molecules arrange themselves into some minimum energy configuration. That configuration is very well defined by the pressure and temperature state. And if you're in this liquid regime, right, we now have the situation where, you know, if the width of that arrow means energy, right? So in the liquid state now, these molecules are jiggling a lot more. In fact, the molecules are jiggling enough that they don't keep these persistent bonds. They slide past each other, but they have weak but important hydrogen bonds that make them still stay sticky to each other, right? So the water molecules can buzz around and slide past each other, but they can't jump up and into the air, right? And so in this regime now, what we know is that if we look at the molecules, that they're in some disordered random configuration, okay? And when we get into the gas state, over here, the molecules are also in a disordered state, but they're less dense, they're further apart. And of course, remember that we have this critical point right here, right? This critical point we come back to time and time again as being this regime where these two phases coexist together, and things are kind of weird, right? By the way, I'll draw that there. All right. So when we talk about this transition then, right? This transition, say, from liquid to solid for water. We've talked about it a little bit already, but we're going to dive into it a little bit more. We're going to dive into it from a dynamical perspective, okay? So let's say that we have a cup of water right here. And we want to take this cup of water and put it in the freezer, okay? So we're going to take liquid water, we're going to put it in the freezer, we're going to cool it down. What we're going to do though is that imagine we have the ability, right? We have a sensor in here. So it's easy to imagine that we have the capability to measure the temperature, we do. But imagine also that we have another sensor in here that we could put in and measure the viscosity. Okay, so we're going to take liquid water, we're going to put in the freezer, and we're going to continuously measure the temperature, and we're going to continuously measure the viscosity as a function of time. And we're going to ask what happens, right? So if you plot the temperature against time, so of course we know at 0 degrees C that the water is going to freeze. And so what happens if we take this glass and we put it into the freezer? So we record the temperature, the average temperature in the glass, and it's going down as it cools, and then it hits this 0 degree mark, right? So at the 0 degree mark, it starts to freeze. The water keeps freezing. There's a freezing front that's migrating through the material, and the material, of course, stays at 0 degrees until all of the liquid water is frozen. Once all of the liquid water is frozen, we can commence cooling again, right? So we're pulling energy out of the cup continuously. When it's in the liquid state, as we pull the energy out, the vibrational energy of the molecules is going down, and so the temperature is going down. But at this point, right, where we're freezing, all of the energy that we're pulling out is being balanced by the energy that's given off as we turn liquid water into solid water, right? And only once that conversion is complete, then we can cool again, right? So you have this scenario, right? And it's the same thing if you're boiling water, right? So if you take water and you heat it and it gets to the boiling point of 100 degrees Celsius, you could keep a thermometer in there and it's going to be 100 degrees till it all turns to vapor. And then if you keep putting heat into it, you'll see the temperature go up again, right? So this part right here is the latent heat thing, right? So materials that crystallize have a latent heat to them, right? They have this, and the latent heat has the effect for us that there's energy that goes into and comes out of the phase transitions. That energy is well defined. And when you try to drive the system across that phase transition, because of the energy cost or energy gain of changing phases, depending on which way you're going, the consequence is that you end up having this regime in the phase transition where you're continuously taking out or continuously putting in energy, but the temperature stays the same, okay? All right, so that part is familiar to us. If we were to look at the viscosity as a function of time, okay? So this is maybe a little more interesting, right? So what happens here is that when we're in this liquid state, right, the viscosity changes with temperature. There's no doubt about it. As we're cooling it, the viscosity is going up when we're in the liquid state. Sorry, let me make this log, because we're going to cover a lot of space, right? So the viscosity goes up gradually as we're cooling it. But once we get to the point of freezing, what happens to the viscosity is this, right? So it's either solid or it's liquid. There's a freezing front. If you're still on the liquid side, you're going to measure a viscosity here. But if you're on the solid side of the front, what you will see is a viscosity jump of 15 orders in magnitude. So the reason I bring that up, right, is, okay, we know that solid ice and liquid ice are very different. But I am here to tell you they are very, very, very different, right? And that there is this discontinuous jump in viscosity, right? So when it's down here as a thermodynamic liquid, it has the viscosity that we know of liquid water, and it's a liquid on our timescales. On the other end of this transition, it is a thermodynamic solid. And from our perspective of experience, solid ice is also a solid. But remember, on geologic times, it is a liquid. It behaves as a liquid that is 15 orders of magnitude more viscous, okay? So the main point here is that when you have this transition, there's a discontinuous jump in viscosity, right? So we call this a first order transition. First order transitions, in this case, refer to a transition in phases that is essentially discontinuous, that is instantaneous enough to be discontinuous. What does this look like, right? If we were just to plot viscosity against temperature, right? So let's do this in an equilibrium kind of way, right? So right now this is a transient situation where we're cooling it, but if we were to ask, take the water, chill it to 10 degrees Celsius, right? What is its viscosity going to be? Take it, chill it to 1 degree Celsius, let it equilibrate. What's its viscosity? Chill it at 0, -1, -2, and so on, right? So if you plot the log of viscosity as a function of temperature, right? So this is 0 degrees Celsius. So up here, you're below freezing. You have a very high viscosity. Right? And you drop 15 orders of magnitude right there at that transition, right? And so, you know, we call this discontinuous. Depends on how finely you measure things, I guess. Is anything truly discontinuous? But this transition, or first order transition, what we're looking at also is it's an order-disorder transition, right? So I want to make the point that when disordered liquids get to their freezing point and they are able to make ordered or crystalline solids, by and large, the transition is of the first order type. that you make discontinuous phase transitions and you have abrupt, dramatic changes in the mechanical and dynamical properties of those materials, right? That's the kind of classic case. So let's think about rock, right? So we'll start with Plato's cube. Why not? Let's imagine a rock. You can imagine it has a bunch of cracks in it. I don't know why I bothered to try and draw it in perspective. Rocks on Earth are pretty varied, but by and large, they are mostly silicates. And so, by and large, they have a lot of silicon dioxide in them. If it's pure silicon dioxide, it's quartz. Other rocks, not minerals, but rocks, are mostly SiO2, and then they have other things mixed in them. I bring that up because we understand then the molecular configuration of the solid state of silicates. I've drawn it in 2D. Of course, they're 3D. They're usually trigonal of some kind. Okay? Remember tessellation? So if we're going to make a crystal like quartz, we have a bunch of molecular configurations. Turns out there's only a few of them that will tessellate and fill space and leave no gaps, right? And so in the case of silicon dioxide, it's minimum energy state. I've drawn as a triangle, but in 3D, it's a trigonal or tetrahedral or pointed kind of thing, right? So let's take rock, a cup of molten rock that is silicate, right? Let's just make it simple. Let's just do quartz, right? Take your favorite quartz grain, melt it, and imagine now you have a melted cup of quartz, and you're now going to take that and you're going to cool it, right? Could somebody shut that door? Sorry, I think Jane just started talking. All right. So if you take this liquid rock, of course, in the liquid state, it's going to be disordered configuration. And as you cool it, you will see, right, a disorder to order transition at the molecular scale. So what does that look like in terms of these plots? It looks the same as water, but the numbers are different, right? So if you take melted quartz and you gradually cool it, what you will find is that there is a freezing point. And at the freezing point, the temperature would remain constant. You have this latent heat effect. And what you would observe at that freezing point is a discontinuous jump in the viscosity. And if you could look at the molecular scale, you would see that associated with that discontinuous jump in the viscosity is a disorder to order transition at the molecular scale, right? So that's all well and good. But this formula here, does anybody else know what other material, common material, has the exact same chemical formula as quartz? Glass. Now, glass means a lot of things to materials scientists and physicists, but to the rest of us, glass usually means like the glass in our windows, right? And the glass in our windows is this kind of glass. And we add some things to it now, but the traditional way of making this kind of glass is that you go out and you find crystalline quartz in sand. You melt the crystals, but then you cool them again. And somehow when you cool them, you get something entirely different, right? So you take a material with the same chemical formula, but if you cool it slowly, you grow nice quartz crystals. And if you cool it quickly, you get the glass that we see in our windows, right? So that's interesting. And if you think about glass, and you look at it now at a molecular scale, so let's say that we take quartz and we melt it, and then we cool it, but instead of cooling it slowly, we cool it fast, right? If we cool it fast enough, the liquid to solid transition is a disorder transition. What I mean is that you could look at glass in the solid state, and if you could image the molecular configuration, what you would find is it looks pretty random, and it looks a heck of a lot like the molecular configuration of the liquid state. And so what's happening in this glass first, we won't say how it's happening yet, but a thing that is happening is that if we take the liquid, the glass-forming liquid, and we cool it very quickly, what we do is we take the disorder that is present in the liquid state and we quench it or freeze it in, right? And so there's this thing, which is that if we cool the same material slowly, it has the time to somehow arrange into a nice crystalline state, but if we cool it very quickly, it doesn't, right? And so we talk about this relaxation timescale. If you want to relate it to something that you can think of, this relaxation timescale is something like, it scales with the viscosity, right? And you can, if you want to think about this dimensionally, what you can look at is that there's a timescale that you take to cool the material, right? And there's a timescale that it takes for the molecules to rearrange and relax themselves under some new energy or stress configuration, right? And if you cool the material really slowly compared to the timescale that the molecules are able to rearrange themselves into some new state, right? Then what you will find, right? So let's say that the cooling timescale is very slow, so we're cooling it very slowly. In this situation, you will make an ordered solid. In this situation, what's that? No. The cooling timescale is very long, right? So if the cooling timescale is very long compared to the relaxation timescale, right? So we're slowly taking the system down to the freezing point, right? And the relaxation time is short, so the molecules can rearrange themselves. So it's like we're quasi-statically forcing the system, or quasi-steadily, meaning we're cooling it slow enough that at every new temperature, the molecules are in a new equilibrium, right? And when that happens, we can introduce the material gradually to the freezing point, and the molecules will say, thank you, I'm now at a point where there's not enough energy for me to slide past my neighbor, and I will find some nice configuration, right? And that configuration is the ordered solid, right? That is the crystalline state. Alternatively, if you cool it fast, faster than the molecules are able to rearrange, right? So, the molecules are jiggling at a rate that is related to the overall energy in the system or the temperature in the system, right? So we're pulling energy out of the system, but if we're pulling energy out of the system at a rate that's faster than the molecules can rearrange themselves, the system is far from being steadily driven, right? So we're now plummeting toward freezing, but the molecules don't have the chance to rearrange themselves when we get to the freezing state before we pass to a temperature and energy that's low enough. So they get locked in a configuration that is disordered. So the molecules are now bonded to each other, and it's not the configuration they want to be in when they're frozen, but they don't have enough energy to jiggle and rearrange and get out of it, okay? So what you do when this timescale of cooling is fast compared to relaxation is that you can form a disordered solid that structurally looks a lot like a liquid. I should mention that fast for silicon dioxide is not that fast, right? If you know about people who make glass objects, right? What you understand is that just taking it out of the kiln and letting it cool in the ambient is still cooling fast enough that you're quenching in the disorder, right? So if you now try to make these kinds of drawings, but you try to do it for the disordered state, you're going to see some interesting stuff, all right? So first, if we look at the temperature of the glass that we're cooling, what we would see is that the temperature is continuously dropping as a function of time. There's no place where the temperature gets hung up, okay? There's no point where it's a liquid and all of a sudden it looks like it's a solid. If we look at this in terms of the log of viscosity as a function of time, what we would see is that the viscosity is continuously rising as we cool the system. And so what you understand is that there's no abrupt jump from liquid to solid. There is a system that becomes gradually more solid-like. And that gradually more solid-like thing is the thing that allows one to work with glass, right? So when you take the glass out of the kiln and it's liquid first, you let it cool a little bit, then you can spin it around a little bit, then you can put it on a stick and swirl it around a little bit, and then when it's even cooler, you can take it in with gloves, you can start molding it with your hands, right? So this is a material that is becoming progressively more solid-like. And so there's no latent heat here. On the one hand, a glass is a strongly out of equilibrium system because you quench in this disordered molecular state in the solid. But in terms of the no latent heat thing, one way you can kind of think of it is that the molecules are jiggling, but they're changing their rearrangements kind of in lockstep with the temperature. Okay? So there's this continuous phase transition toward the solid state. And if we plot instead, right, our steady state diagram of looking at like the log of viscosity as a function of temperature, right, what we see is something like this, right? Is that the viscosity is continuously changing with temperature indeed. There's no discontinuous jump. However, there's this divergence, right? So as we cool the system closer and closer to some glass temperature, we have this situation where the viscosity blows up. And when the viscosity gets big enough, the timescale gets long enough that we can't effectively measure it experimentally, right? And at that point, we call it a solid because it's a solid on our timescales, it's a solid on experimental timescales. That then means that there's this glass temperature, but this glass temperature isn't something that we can predict from first principles. It's typically not something that we can measure directly either. We have to infer it by the viscosity that we can measure, right? So this timescale is blowing up also, right? So the timescale you need to measure it over in order to measure viscosity is blowing up as you approach the glass temperature, which means that, you know, what this says is that the viscosity goes to infinity at the glass temperature, and that's when we then say it's a solid, but we can't get anywhere near infinity, right? So mathematically, you can write an expression that says that the viscosity is going to scale something like the temperature difference from the glass temperature, right? So it's going to be like the temperature, if we're above the glass transition, the viscosity goes like the temperature minus the temperature of the glass transition to some negative nonlinear power, right? So this thing should indeed become infinite, right, when the temperature is equal to the glass temperature. So what you actually do experimentally to figure out the glass temperature, because we don't have good equations of state or fundamental understanding of phase transitions for disordered materials. We can't do all the thermodynamic stuff that we do for nice water crystals, right? So if we want to know this glass temperature, what we do is we actually measure the viscosity as a function of temperature in the places where we can measure it. And then we fit some divergence equation like this, and we have to fit the glass temperature, right? So different materials have different glass temperatures, and those glass temperatures indeed depend on the details of the system. But we can't know them a priori, and we can't measure them. We have to extrapolate to them, okay? Because the dynamics are really slow. Now, I played this game with quartz, which I said, or silicon dioxide, which could be solid crystalline quartz. It could also be solid amorphous glass. You might reasonably ask, okay, wise guy, what about some other more common material like water? So water, as we experience it on planet Earth, is almost always in the crystalline state. Only under very extreme conditions do we see amorphous water. But you can make amorphous water. Turns out, if you take water vapor and you introduce it to a chamber that is cooled to close to absolute zero, it will freeze so quickly that it makes non-crystalline water. So crystalline water is what we have in terms of ice on planet Earth, but amorphous water ice is almost for sure what is dominant in the universe, okay? So I just wanted to make that point. Let's make this a little bit less abstract. Let's now think about not thermal examples, but we'll think about examples of particle systems that we can see. And we'll see whether or not these concepts translate to those, all right? So the way that I want to do this is with some oranges, right? Yeah, that's exactly the reaction I wanted to get. Confusion. If only. Okay, there's the beautiful hand I got right there, right? Here is the hand of God. Yeah. At the grocery store, stacking oranges, okay? So you want to stack oranges very carefully, right? So here's these oranges, you place one, then you place the next one, and then you carefully place the next one, right? And so you're taking a lot of, next you come back with a new orange and you say, oh, I want to place this thing in a place where it doesn't roll. You search around, you carefully find the minimum energy configuration where it's sure not to move, and you place it there, and you place another one, and you place another one, you place another one, right? And so if you take all of the time in the world, you can carefully stack the oranges, right? And you can build a crystalline orange pyramid, right? If you look at this configuration, right, you will understand that this is a macroscopic example of a crystal, okay? So you can, if the oranges are similar enough in diameter, which they usually are, even a little bit of disorder in their size, you can overcome and you can make a nice ordered pack. That ordered pack of oranges, by the way, also takes up the least space, right? This minimum energy configuration of oranges, the crystalline stack of oranges, its minimum energy, the oranges won't roll away. That's why we do it. And it also is volume saving, right? It takes up the least amount of space. That's why we do it. So, okay, what's the fast version, right? What's like the lazy fast version? We have a box of oranges up here, and we just tilt it and dump it, right? So I think all of you would be surprised if you tilted and dumped your oranges and they ended up in this nice, beautiful packed state, right? We all understand that if we just dump the oranges, they're going to have some jumbled configuration to them, right? It's going to be a disordered pile. The disordered pile is a little more fragile. It would be easier to like take an orange out and send the whole pile tumbling down. And it will also take up more space because there's going to be more holes in here, right? And with this example, what you understand is that slow placement creates this ordered crystalline arrangement, and that a fast quench, if you will, right? Or like fast placement is going to create a disordered system. So in principle, if we think about sand or soil or particles out in nature, I guess you could have either one, right? You can imagine if sand grains were uniform enough that you might sometimes find them in an ordered state, and you might sometimes find them in some jumbled, disordered state, and that it depends on how nature prepared them. But it turns out that if we think about soil, or even just sand at the beach, which is disordered enough to do it, it's that you have heterogeneous mixes of particles, okay? So particles in nature, sand, gravel, boulders, clay particles, whatever, they are almost without exception sufficiently varied in their size or their shape or in both, such that they are always disordered, right? So it's pretty easy to show that with a sufficiently varied particle size distribution alone, you frustrate the ability to make a crystal ever. And if you frustrate the ability to make a crystal ever, that actually means that you frustrate the ability to have a clean first order transition, right? So we know that sand can behave like a liquid, and we know that sand can behave like a solid, and we know that it's not a thermodynamic liquid, right? It comes from injecting mechanical energy from the outside. But this statement here, that the soil is essentially always going to be disordered, means that we can never have the clean first order transition from a solid state to a liquid state and back with something like natural soil. The other thing that it means then, which is a little less obvious perhaps, is that there's either no minimum energy configuration, meaning there's no exact arrangement of particles that will guarantee you that the system is the most stable and lowest energy. Or another way to say it is that there are an infinite number of configurations that would produce the same energetic state or the same macroscopic stability. So why does that matter? I'm going to show us now, like, with a simple example, why that might matter. And so remember, we're interested in this lecture in the creeping regime. So we're interested in this lecture in things that are apparently mechanically solid and yet dynamically are deforming, right? So let's think about creep in a crystalline material, all right? So what we have is, let's imagine that we have, we're doing a little ball and stick drawing, right? This is a little ball and stick drawing of, you know, molecules as balls and sticks. And let's say that this is a crystalline solid. And in this crystalline solid, I introduce a hole somewhere. I introduce a defect. So all these molecules are bonded together. They're bonded in a minimum energy configuration, which means that they're vibrating the least. If I deform this sample, right? So I'm shearing the sample now, and I'm going to force the sample to deform. So the sample has to respond by reconfiguring, right? So these bonds will get stretched until they break, right? If it yields. But it has holes in it. If I introduce a hole, what happens is that if I apply deformation at the boundaries, the major way that this material is going to accommodate that deformation is that this hole is going to move. So at time 0, I have a crystal with a hole in it, and I apply some shear to it. And at some later time, T1, when I look at it, what's happened is sorry, let me connect these just for consistency. The hole is migrated, right? So the way that creep is accomplished in solid materials, the way in which you can force a solid material to deform, but it can respond and it can deform without breaking, is that defects migrate. And in a crystalline material, it's the migration of these localized defects through the material that allow it to accommodate that deformation without macroscopically yielding or breaking, okay? And so, I don't have the time or the space to get into this now, but what happens is these defects move through, and when the defects get to the end of the crystal, they disappear. So creep is accommodated by migration of defects. And when those defects get ironed out or annihilated, you harden the materials. And so there's this process of strain hardening. And strain hardening is the thing where by applying strain or deformation, you activate these defects, but the defects migrate through the system until they get to the borders and they leave. And when that happens, you've made the material harder or stronger, okay? So this is a phenomenon that happens in crystalline materials all the time. So what about now if we try to do this with a disordered or an amorphous solid, right? So let's say that I have some configuration, some disordered jumble of molecules or oranges or whatever I want. And then I make a hole. I introduce a defect. It's very hard to predict what's going to happen in response to that, right? So I apply shear to this system, and it's going to accommodate that by defects moving through the system. But if I get a little bit of deformation, I introduce a hole or something like that. Well, sometimes I might activate a localized rearrangement. So imagine that there's like a little cloud of particles in the vicinity of this hole that I've introduced. So I might activate some little rearrangement. So I'll say that there's a length scale of rearrangement that sort of captures the scale of the rearranging particles, right? So I can introduce this hole, and sometimes there's going to be a little rearrangement. I release the stress, and I reach some new configuration that is stable enough. But sometimes there's going to be some cascading domino effect where introducing a hole or a soft spot or something like that causes the entire system to rearrange, okay? So even though I might introduce a defect with a well-defined scale, like a hole, the rearrangement that happens in a disordered system is not well characterized at all. The same hole size that I introduce, either at different places within the system or at different times in its deformation, can excite a big range of length scales of response, from little localized rearrangements in the neighborhood of the hole to ones that propagate all the way up to the size of the system, right? And so, first of all, that is a key part of fragile, right? This disordered system is fragile in the sense that a minute change in the microscopic arrangement of the particles can produce small or intermediate or large, even disproportionate responses. And also, after rearrangement, the particles find themselves in a new configuration, but because they can't make a crystal, that new configuration is also not guaranteed to be stable either, right? So these systems can be rearranging in unpredictable scales in unpredictable ways. Okay, so if you think about this now, in terms of the system's ability to respond by straining under a load, okay? So if we think about our sand pile at the beginning, what happens is that you could say, all right, this will be plotted in log space, okay? So particles with small, or rearrangements that happen that are small in their length scale, you could say then that there's a time scale of relaxation, right? So when I cause a small rearrangement, what I will do is excite a creep rate that will initially be fast, and it will die off exponentially. Okay, so I've strained it, and I get a local rearrangement, and it rearranges fast in the beginning, and then it settles itself down, right? So if I have a small length of rearrangement, I will have an exponential relaxation in the strain rate that is small. If I have, I'll draw a small cloud here. If I have an intermediate scale rearrangement, more particles are involved in the rearrangement, then what I'm going to have is a longer time scale of relaxation, okay? And if I excite an even bigger length scale of rearrangement, it is going to cause an even slower and longer relaxation time in the experiment, right? So now this material does not have one intrinsic relaxation time, because the relaxation time is actually tied to the scale of the rearrangements, or the number of particles that are involved. So I could fit one exponential to the relaxation time for the small rearrangements, a different exponential for bigger ones, a different exponential for bigger ones, and so on. Well, it turns out that I have a power law distribution of rearrangement sizes. Remember, we talked about things being power law and scale free and all that stuff. And that means that if I sum up all of these different exponentials, what I end up with is a power law relaxation of the material, okay? So a crystalline material, if you wanted to measure the relaxation timescale, you would perturb it, and then you would measure the responding creep rate, and it would drop very quickly. When you take a disordered system and you do this, you're exciting all of these different length scales of rearrangement, all with their own time scale. And what you end up with is the situation where the creep rate under an applied load, the creep rate of the material decays as some power law function of time. And in principle, that power law function of time is related to the power law distribution of relaxation timescales, which is related to a power law distribution in relaxation lengths. All right? And so this kind of creep test, we know that all kinds of glass materials follow this kind of creep relaxation. So if I take a piece of glass and I apply a static load to it, like I squeeze it and I hold it and I just let it creep, I will see this power law decay. You know what else does it? A pile of sand. If I just pour a pile of sand on a table and I let it sit there, in the beginning the creep rate is fast, but it's rearranging, the particles are rearranging and finding lower energy states. And so when that happens, it slows the creep rate down. But I keep getting ever lower energy, but I can't quite get there, right? And so the last major concept that we need to introduce here then is kind of coming up with a conceptual picture about how this order-disorder or disorder-disorder transition relates somehow to the structure. I've kind of hinted at it, right? I've said that an order-disorder transition is going to create a first-order transition in terms of liquid-solid. And I've said that a disorder-disorder transition is going to make things continuous and second order. So I'm going to go out on a limb a little bit, because we're going to, I mean, these are already cartoons, but I'm really going to get into the land of metaphor now, right? So if I think about the crystalline material and the disorder to order transition. So one way that I can think about it right, is this idea of an energy landscape, okay? So let's imagine here that I have some axis that I'm just going to call configurations, right? So this is just going to describe statistically or deterministically, this is going to describe like different arrangements of molecules in my material, right? And up here, let's just say the y-axis will be a thing that I call energy, right? So there's this idea that there are all kinds of different configurations that my molecules might take, but there's one in which the energy in the system, for our case, we'll think the vibrational energy, the molecules or something, but is at a minimum, right? So now, if I pump a lot of energy into the system, so let's just say it's a hot system and it's in the liquid state, the vibrational energy of the system is large and all of them will be above this configuration. But now I start to cool the system down, right? So I'm lowering, as I start to cool the system down from the liquid state, I'm bringing the energy down, right? And you can think about it like a flood, that when the flood is here, there's water everywhere. But as the flood waters come down, right? I imagine that I'm on a boat here that's moving along, but as the flood waters come down, where am I going to end up? In my little boat, I'm going to end up at the bottom, right? The premise here is that when I think about this disordered to ordered state as I cool a crystal forming material, is that when I have a lot of energy in the system, all configurations are possible. But as I lower the energy in the system, then there's this well down here, there's this well-defined configuration where the internal energy of the system is minimized. And as I lower the energy in the system, the particles are going to glide toward this configuration, right? So in a crystal forming material, I have this minimum. And if you want to think about what happens if you dump energy in, one way to think of it is like I tilt the energy landscape, right? So you say, now I have a solid crystalline material with a well-defined minimum energy. And sorry to mix my metaphors, but I can think of it as a ball right there, right? And so what you understand is like, if I'm tilting the energy landscape, I'm driving the system harder and harder, but the system says, I'm happy to stay here. And at some point, I tilt it too far. And when I tilt it too far, the ball abruptly rolls out, right? And so what you understand is that if there's a well-defined minimum energy state, the system will sit in that state under a range of energies until the energy is too high, and it will fairly abruptly jump out of that state, right? So now, what we want to think of is, let's take a disordered material, okay? So one way to think about a disordered material is that it has a complicated energy landscape, okay? So imagine that you have, this energy landscape. You think of it as like the water level's up high in your boat, and you're cruising around in your boat, and then it starts draining, right? So you might get caught here, but if the water level were to rise up again and you cruise around on your boat and then the water level drop, you might end up over here, right? Or you might end up over here. In the way I've drawn this energy landscape, there is a minimum energy configuration, but there's a lot of other local minimum energy configurations, and there's a high probability that if you bring the water level down, and especially if you bring the water level down quickly, that you will get caught in one of these minima, and they will not be the global minima. And what you realize is if you're stuck in a local minima, it takes a certain amount of energy to lift you out of there in order for you to explore the space and find another configuration. Now, imagine that you take this system and you tilt it, right? So now, if I have a ball sitting right here and I tilt it, it'll sit in this configuration and then maybe it'll hop over here, but then it'll get stuck down here. And then I probably have to tilt it a lot more to get it out of here, but then it might just get stuck in the next one, right? And what you understand is you're driving the system, and it's not like there's one point where the ball jumps out of the well and just starts rolling like crazy. The ball might jump out of the well with a little bit of tilting, but then it might get stuck in a well where I have to tilt it a lot more, but then get stuck in a well where I tilt it a little bit more, okay? So the point then is that the system can get caught in a bunch of local energy minima, and the system gets uncaught a bunch of times as you try to take it from like the solid to the liquid state by like tilting this energy landscape. And so what does that look like then mechanically? So this one, if you think of it in terms of a solid material, right? So we'll do our classic like stress strain diagram, and we'll do it for a nice crystalline material, right? Mechanically, this is what it looks like. It's an elastic-like solid, and then at some point you get to yield, and then it just catastrophically loses all its strength, and it falls to bits, right? So mechanically, it has a first-order transition, right? And that is related to the first-order transition in the dynamical and thermodynamic behaviors of this crystal-forming material, okay? If you take the disordered system, and you say, if I take a system that is disordered with this kind of energy landscape, complicated one, and I start driving it, I apply a load to it, I'm squeezing it or something like that. Well, now it's going to have macroscopically a stretched out failure envelope, right? It's not going to like just build up stress and then fall apart. It's going to have many rearranging events that happen at a bunch of different strains. Essentially, the things that are have these complex energy landscapes tend to have more ductile failure kind of behavior, right? And when you look at these curves, you look at the trade-offs, right? So ordered systems will typically have high stresses, yield stresses, in which they fall apart, but they will fall apart catastrophically. They will abruptly change from one state to another. And systems with highly varied or disordered energy landscapes will tend to yield at lower stresses, but you will tend to stretch that yield out over a broader failure envelope rather than them catastrophically falling apart, right? If you want to think about this then instead in terms of the liquid view of things, so like viscosity, right? If we think about it in terms of plots of viscosity on the y-axis, on the x-axis, we'll plot log of, it'll be temperature if it's a glass, or it will be stress if it's a granular material, right? And what you would see is that, the crystal forming materials, of course, have these first order transitions in the temperature viscosity space. And these ones look something like this, right? These are the glasses that diverge as you cool them, right? So now I need to be clear. This energy landscape argument you can make pretty directly for true glasses, meaning glasses where the bonds are molecular bonds and that have some internal energy, like vibrational energy to them, right? So like that the molecular bonds in the molecules of glass in the window are shaking with some internal energy. If we think about the sand pile or the oranges, they're big particles. They're too big to experience thermal vibrations, right? I mean, they sit here in the air, but their mass is such that they don't have any intrinsic vibrational energy. You cannot directly use the energy landscape framework for them because they do not have an intrinsic internal energy to them. However, it turns out that the conceptual framework of the energy landscape, you can extrapolate from thermal glasses, and it actually is useful for interpreting and understanding athermal systems. It actually turns out, as I hinted at before, that there's a deeper similarity between athermal large grain systems like sand piles and thermal small particle vibrating internal energy systems like glass. And that is both mysterious and beautiful, right? Now, I don't want to make this picture too simple. I do need to put wrinkles in it a little bit. While it is generally true that disordered materials are more ductile than crystalline materials, it is also true that some disordered systems are more or less ductile than other disordered systems, right? So I don't want you to get the idea that all disordered systems are here and all crystalline systems are up here. And I don't need to look any further than the sand pile to get an example of this, right? So we talked about the sand pile creeping before. And in the beginning, we have this loose, fluffy pile of sand sitting under gravity. And as it creeps, the grains rearrange and it finds itself in some lower energy configuration. And what that looks like is if we plot the strain rate, essentially the rate of internal deformation as a function of time, we know that in the sand pile, just like in glass, it decays as a power law, okay? But the other thing then is that if we plot something like the yield stress of that pile of sand. So we said, how hard do I need to load the pile of sand for it to fluidize? We know that that goes up as a function of time. So strain hardening is happening in the sand pile, right? And the strain hardening is making it so that the yield stress is going up. But the other thing that happens is that I transition through time in the sand pile from this to this. So as the sand pile is creeping and strain hardening, I'm working out a lot of the scales of soft spots and rearrangements, right? And so because I'm working out the weakest links, I'm ironing them out, the strain rate is going down. Because I'm working out the loosest, floppiest parts of the pile, the yield stress is going up. But I want you to know that not only does the yield stress go up, the overall strength, the mechanical behavior of the system is changing. So the initial loose pile of sand is very floppy and ductile. And as it strain hardens, it becomes stiffer as it becomes stronger. Okay? So even disordered materials can transition from brittle to ductile. And it has to do with whether or not the material has access to all of the different scales of rearrangements, if it has a lot of soft spots and weak regions to rearrange, or whether you worked out all the easy ones and only the hard ones are left. So in the sand pile in the beginning, it has easy and hard configurations to rearrange and overcome. Just sitting there under gravity and maybe gently being kicked by whatever tiny vibrations there are, all the easy, soft zones, all the ones that rearrange the easiest, work themselves out first. And now you have a system that needs a bit more energy, maybe a fair bit more energy to cause more rearrangements. That makes it more brittle. What that actually means then, in terms of the energy landscape, is that in the beginning, let's say at time 0, I have an energy landscape like this. That creep itself is changing the energy landscape, right? So if I'm saying that rearrangements eliminate some configurations in some wells, you sort of have this thing over time where you can imagine that the energy landscape is changing, and at all of these different wells, it's kind of getting smoothed out, that some of them are going away, right? The energy landscape will always remain disordered for the sand pile, but it's not the same, right? And so The energy landscape, as we think of it, can dictate the mode of failure, but the energy landscape itself evolves as the material configurations evolve. So this is some rather like abstract, like mumbo jumbo, right? And to close, I do want to bring it back to actual landscapes, right? So, you know, if we think about our soil on the hillside now, right? You can ask, why does all the stuff I've talked about matter for landscapes like this, right? So we know that the sun comes and goes away, it heats the soil, cools the material, right? We know that we have wetting and drying, the addition and subtraction of fluid stresses. We have heating and cooling, right? Freezing and thawing. That's my little bad snowflake, right? We know that we have shaking and earthquakes on the system. Heck, we have wind stress directly. We also have just changes in barometric pressure of the atmosphere, which we actually know cause soil to like breathe. Changes in atmospheric pressure can cause the soil to expand and contract and speed up and slow down in its creep, right? So we have this mechanical granular system that is creeping, and it has this very complex energy landscape where sometimes we can inject a lot of energy and affect little change in the soil, and sometimes we can inject just a little bit of energy and we can affect a lot of change in the soil. Under all of these mechanical stresses, what we know is that, like, just the strength or the yield stress of the material, if you could imagine that we could measure this in soil and take a time series of it, if you could measure the mechanical strength of the yield stress of soil under the barrage of all of these environmental loads, you would find that that yield stress is this complex time-varying thing, right? So the mechanical strength of the material itself is evolving under creep and under these loads. But understand also that it isn't just overall strength, that you can also change the soil from being more brittle to more ductile and back again under these kinds of drivers and transformations, right? Now, this is especially interesting and especially frightening when you remember that landscapes are perched at the yield stress, right? Remember, everything's critical, right? Everything's threshold, and threshold is everything. And so you have this mechanical properties of the material changing as it's creeping, and then you also have applied stresses that are time and space varying. And we know that when the applied stress exceeds the internal stress, that it will fluidize and make a landslide. But we have a situation where the applied stresses are fluctuating, but the internal resisting strength is also fluctuating because of mechanical deformation. So creep rate, we know that the landscapes are perched close to the yield stress. We know that the creep rate changes dramatically in the vicinity of the yield stress. It's a continuous but rapid phase transition. It's this diverging thing. Creep may harden or soften the soil. So this means that changes in the yield stress are going to be really hard to register and really hard to predict. And so soil on the hillside is a classic example of fragile materials, and it's why I say that earth is fragile, because this soil will not stay how you put it, right? It might be generally in the same place when you come back in a month or a year in the bulk, but it will not be in the same configuration, and then will not have the same mechanical properties. So that's where I'll stop it for today. Yeah.
really sure if I'm understanding this correctly, so bear with me, but I'm thinking about like the definition of a material that creeps versus one that fluidizes. Like, is there, if I'm observing a material and it appears to, like you said, not be moving over time, we can say that it's still creeping, but like I guess like how slowly does it need to be like not moving, or like how quickly, like to define it as something that creeps versus something that fluidizes? Like, could I come back in a day and it's like moved very slightly, and then I'm like, okay, well that's something that fluidizes versus creeps?
Yeah, so no, I mean, this is not a naive question. This is like the question at the heart of it. I mean, I've kind of answered it, but not really. I've kind of given you a bunch of things, though, that we might be able to thread together to answer that question. Okay, so I'll remind us first that, let me think of a Newtonian fluid. Water and air are Newtonian fluids, but honey is a Newtonian fluid also, or Newtonian enough. Why do I bring that up? Because with a Newtonian fluid, the thing about Newtonian fluids is they flow under any finite stress, right? You know that water will flow as long as the stress is non-zero. Water will flow, right? The moment you try to tilt liquid water, it's going to flow. The difference then, I'm saying, like, if honey and water are both Newtonian fluids, what's the difference? It's just viscosity. So the honey will also flow at effectively zero stress, right? As well, not zero, but close to zero, right? As long as the stress is above zero, the honey will flow. And the viscosity just says that it will do it at a slower rate or a longer time scale. So in those situations, something flowing slowly doesn't have to mean that it's creeping, right? And in the case of like honey and water, which are Newtonian fluids, the important thing is they have no yield stress at all. The part about saying that when they're in their liquid state that they will flow no matter the stress, what it means is they have no yield stress. And with honey and with water, it is only when you bring them into their thermodynamic solid state that they now are a solid that has a yield stress. So like the honey or the water will flow as a liquid at any stress, any non-zero stress. But once you solidify them, in order to make them deform, right, you squeeze on them and they will have a yield stress at which they'll fly apart. So they've got no yield stress when they're a liquid, and then they have a yield stress when they're a solid, right? So if we now think about sand or toothpaste or something like that, these are materials that they can flow or not flow, and it's not related to temperature, right? They can flow or not flow because of an applied stress. So if I think about sand or toothpaste, there's a range of stresses above zero where it is still not flowing like a Newtonian fluid. But if I drive the system even harder, at some point it will change its rigidity, right? So the toothpaste will lose rigidity, the sand will lose rigidity. So in those systems, there's a well-defined yield stress. And when I drive the system beyond that yield stress, I call that fluidizing. And the stuff that it does when it's below its mechanical yield stress is what I call creep. Okay? So it's not like an issue of like raw time scale, right? That kind of brings us back to that phase diagram that we made. It's this part where these are materials that have a yield stress, and above that yield stress, they do what any of us would call flow, and that's the fluidized region. And below it, they're doing this thing where they appear to be solid by some mechanical tests, but they are deforming. Do you know what I mean? And the real distinction then is this idea of a yield stress. Fluids that don't have a yield stress are not gonna like do the kind of creep that we're talking about for all these amorphous solids. Yeah, Nandish.
Not to be devil's advocate, right? But if you have this yield stress that is changing over time,
yes.
Is it not then easier to think of the perspective of accumulated strain, right? So now you're talking creep is some level of flow that is happening below like some yield, right?
Yeah.
But you're also saying that yield stress changes over time.
Uh-huh.
So I feel like it's kind of going in a circle over here that like, yeah, you're creeping some yield, but then that creep itself changes what the yield stress is, and then you get some sort of fluidization. Fluidization process. So then the description of the yield stress is now certainly iffy.
Correct. Okay, so just for everyone, right? There's a question about like strain or accumulated strain or strain rate or whatever. I'm going to transport us back to lecture 1 for a second, right? So, we draw these diagrams. We say, okay, when we do a solid mechanical test, we plot stress against strain. And when we do a test for a fluid, we plot stress against strain rate, right? And it's kind of a subtle thing about why we do those two things, right? But it's related to the de Boer number kind of argument, right? And so the thing about like liquid water is that the relaxation time is very, very quick. And so essentially what happens with liquid water is that when we shear it, the molecules are tiny, they deform easily. When you shear liquid water, the hydrogen bonds are easily broken, but they instantly reform new ones, right? And so when you think about a material with a liquid, the thing that is a liquid, for a mechanical test that has a very short relaxation time scale to it, right? So we can't even measure accumulated strain before the molecules rearrange, right? It's nothing. We also know that that in that liquid that the bonds get reformed. And so the way to think about like the mechanical liquid like water is that you're continuously forming and breaking and reforming bonds as you deform it. And the relaxation time is so fast that it makes sense for us to do mechanical tests that look at stress against strain rate, right? When we think of the things that are mechanical and dynamical solids, we're like, first of all, the relaxation time is very, very slow. So you take a rock, no one wants to do a strain rate sweep for a rock, right? And you wouldn't see much because no matter how much strain rates you could cover in your rock experiment, you're not gonna like touch the relaxation time scale of the rock itself, which is very, very long, right? And so the molecules are essentially taking infinite time to reconfigure themselves compared to any deformation rate that you're gonna apply. Since you're in that limit, you say, actually, then it's independent of rate, right? The relaxation time scale of the molecules in the rock is so long compared to the rate that I'm deforming it, then I'm going to assume that the rate that I'm deforming it doesn't matter. And therefore, I'm going to look at stress against strain, right? And when I deform things enough, the internal relaxation rate is very, very slow. And bonds can reform, but that takes pressure and temperature and is also really, really slow. So when you break bonds, they stay broken and the material flies apart, right? So what you understand then is that in the clear case of like solids and fluids that are very different from each other, the mechanical tests and the variables we use are very different for good reason. The discomfort with soft materials, right, is that they're both solid and fluid, right? And they have solid-like and fluid-like characteristics. And if their relaxation time is in the middle, it can make sense to do both solid-like tests where you would look at accumulated strain, but they do, like sticky soil does reform cohesive bonds when you deform it. It doesn't necessarily irreversibly break them and make cracks. And so, like when you think about like a polymer gel or something like that, you can shear it and you can stretch and break the polymer bonds, but then they can also get tangled up and reform again. And so in some kind of like polymers, it doesn't really make sense to look at cumulative strain. They're behaving more like the liquid state. Like you're breaking and reforming them all the time. And so what you want to do is look at the behavior over a bunch of different strain rates. But in a real stiff polymer, that might not be the case, right? It might be more in the solid-like regime. And I know I'm dancing around in circles, but like that's the kind of thing that I'm facing with the soil is that it's kind of solid-like and kind of fluid-like. It's in that soft middle ground. I would be very comfortable with the cumulative strain to failure that you're saying if it didn't reform cohesive bonds and frictional bonds, but it does, which means that it's not that it's necessarily going to fail globally at some cumulative amount of deformation. It might and it might not. You know what I mean? And so that's what makes it tricky.